So I was invited to tell you a bit about phenomenology. So I don't know if I did a good thing, but I prepared the talk as sort of a presentation of phenomenology in general. And at the end, I will tell you what I'm interested in and what I'm doing right now, of course, qualitatively. I know this room is very bad. So if you really do not hear me, I don't know, raise your hand or I don't know, like, don't be afraid to interrupt me, okay? So what is phenomenology? So if you check on Wikipedia, it will tell you that, so in physics is the application of theoretical physics to experimental data by making quantitative predictions based upon known theories. So this is the first keyword, is about making predictions. And then it says that it's commonly applied to the field of particle physics, where it forms a bridge between the mathematical models of theoretical physics and the result of the high energy particle experiment. And this is really what we did. So it's really like the field of research that stays in between. There's really a broad spectrum, almost a continuum of research between the theory and experiments. Sometimes we are experimentalists do very similar things. Sometimes we do things that are more similar to theories. So you have these two directions where you have Lagrange's and mathematical formulations on one side, and then you eventually have something like events on the other side, and the phenomenologies make the two talk to each other. So before I can tell you what we actually do, I think it's good to know what people are doing in general. So what is the status really in IMAPP? What do people talk about? What are the topics? So this is a very, very broad introduction to say that, been a few thousand years that we have started to study physics and to develop theories. First there were philosophies, then there were science about nature and what comes around us. And as a humankind, we have rich knowledge over many, many different energy scales. From the very, very large, where we think we have a guess of what is going on in the universe, why it is expanding, although we still have many questions, down to the astronomy. You can have planet science. You can have things that go into medicine, into atomic physics, nuclear physics, and eventually particle physics when you reach the scale that is around here, right? So around the 10 to the 19. 10 to the minus 19 meters, roughly, if you put the count with the Planck constant. So there is a barrier of this quantum world that we have crossed about a century ago. And this is where we made it. And we have a guess that something must exist at least on the other end of the spectrum, because we have gravity. And if you calculate the numbers with gravity, you will see that supposedly it should happen at an energy which is 10 to the 28 electron volts, which is 10 to the minus 39, 34, sorry, in terms of meters. But we have no idea of what is in between. So particle physics lives in this band roughly around the yellow part, around there, where we have the standard model. And the standard model is a theory that is super successful. Honestly, it's really one of the most successful, most tested theories ever to a really high level of accuracy. So this means we really know, we understand what is going on in 90% of what we see at high energies in the band that I just showed you. But at the same time, we're not convinced that this is over, so that this is the ultimate theory of nature. And if you want, there are three categories of reasons. So one is the merely philosophical reason of there's no justification for why this particular energy, the one that we have reached in this point in time, is different than the others. So we just made it so far, then there should be something else, why not? And then there's the fact that there are some experimental observations which are not really included in there, for instance, like matter. Neutrino masses technically are not part of the standard model either. Some observations in the universe, so we're made of matter and not antimatter. In principle, both could have been possible, but something happened early on in the universe for which only matter survived. And there is nothing there is not enough in the standard model to justify this observation. And then there are some theory aspects that are not really nice. For instance, one is the hierarchy problem, which is a bit even a little bit controversial, but the point is that essentially we wonder why we live at this scale. We just said it is not special, so there is no mathematical justification for why this particular energy should have been chosen. And then other things, for instance, the fact that you have three families for all the fermions, you probably see that you have electrons, muons, and taus, and you have ups and trims and tops, and so on and so forth. Why? Why do we need to have three? This is also completely unexplained. We know we have three, but we don't know where they come from. So the baseline is that we all think that there must be something beyond the standard model. We have this quite motivated suspicion, but at this point, we don't really have a clear indication for what it is, where it is, what it should look like. So there are three main things that we do with high energy physics today. So one is that, I mean, we understand 99% of the processes, but it doesn't mean that they're uninteresting, right? So there are still some processes that have been predicted by the standard model, but we have not measured yet. So that's some research that goes towards observing some stuff for the first time, because we know it has to be there. One example is the production of composite states of 4 quarks that are called tetra quarks. It's something that is not taught in the courses, but they exist, and there are experiments that are producing them quite a bit lately. Another example is the production of 2 Higgs bosons in colliders. So we have not observed the self-coupling of the Higgs boson yet. Could be there, but we haven't touched it. There are also other processes that are just rare, and they don't happen very often. So they need a lot of statistics and a very sensitive instruments. There is also an aspect of measuring parameters that are unknown. And now this technically for the standard model, there is nothing left unknown. We have measured all the 19 parameters that it has. But if we just extend the standard model a little bit, the neutrino masses are there. So we have established that neutrinos are massive and that they mix in flavors. But surprisingly, there are still some questions that are not answered. So for instance, we know that there are 3 neutrinos, and there's a mass difference between 2 of them and another 2 of them, but we don't know in which order they come. We don't know if the lightest is exactly massless or not. We don't know if there is CP violation, so the equivalent of the CKM phase for quarks is also present in principle for neutrinos, but we don't know if it's there or not. And there are experiments that are measuring all these aspects, or going towards the measurement of these aspects right now. And then the last is the obvious, so like, okay, fine, but we want something new. And there are different ways to look for something new. So something new could be a new particle that we produce, and this has to be a collider. So the only way that we can discover a particle is that we smash things and we produce it. It can also be, however, that we haven't found something which is light, so it's not a problem of having enough energy. It's a problem that the particle does not interact very much. This could be the case of dark matter, for instance. So if you have a mass that is easy to produce, but then the interactions are very low. So this requires really super sensitive experiments. Or another thing is to generically stress test the standard model. So like shake it until it breaks and understand where does it break. So look for any tiny inconsistency with the predictions, any breaking of the symmetry, any violation of the interactions, difference in interactions that are observed. So experiment-wise, the landscape is roughly divided into 2 categories. So one goes into put a lot of energy. And this is the thing that I will talk the most about. So the energy frontier nowadays is essentially the LHC. So this is an accelerator of protons, let's say that sits at CERN in Geneva. It has 4 large experiments. They are in the map there. So the map has some perspective, but they are at 4 corners. So there are 2 general purpose ones, which are called Atlas and CMS. One is here and one is there. There is LHCb, and then there is Alice on the other end. And they also have 5 smaller that are sitting around. 4 of them are near each of these detectors, and they do slightly different physics. So these are the guys that can discover particles if they are produced. The way that it works, that is match 2 protons together. Inside the proton, you have the quarks, you have the gluons, mixed up in some way. So in the high energy collision, what collides is really, for instance, the gluon or the quark. And then in this collision, you can produce a particle that did not exist before, for instance, the Higgs boson in there, and then the particle typically is unstable, so it decays. And so this is the process of smashing two gluons and producing four leptons. But in between, there was a resonance that you can detect, and this is how you discover a new particle. So we tried it to see if something else apart from the Higgs boson was produced, but so far, nothing really came out. The other directions of experiments is the intensity frontier. So instead of smashing towards more and more energy, we go to more and more precision. And here there is a lot. So I wrote down a few names, but there's like hundreds of experiments because they are, compared to the LHC, they are cheaper to make, they are smaller, and so it's easier for many more groups to try out different things in several parts of the world. While the LHC, there can only be one giant accelerator at a time because it takes up a lot of manpower and a lot of energy. So in the intensity frontier, so there are many. So the classification here is a bit arbitrary. So many of these experiments do many of the same things at the same time. But there are some that go towards, observing new phenomena, for instance, meson decays, or some other processes that are rare, and so they have not been studied very well yet. There are all the neutrino experiments, and you see one example here. This is the CP phase in the neutrino plane compared with one of the mixing angles, and this is one of the plots that are produced by one of these most recent experiments. So you see that these are slowly kind of identifying, so coming to a measurement in all the parameters. So these are preferred regions. So we do not have a value, we have kind of an error band. Then there are experiments that look for really rare phenomena, and the idea is that these phenomena are predicted in the standard model, but they are predicted to be very, very tiny. And so if there is new physics, it could be that we see them much larger than what they are in the standard model. So they're very good probes for the stress testing. So some of these processes are so anomalies in the general magnetic moment of the muon, or for instance, the existence of anomalous electric dipole moments and magnetic dipole moments, or the neutrinoless double beta decay. If you ever heard the possibility that neutrinos are Majorana, this looks for a process that violates electron number. So it can exist if neutrinos are Majorana, but even then, it's super tiny. And so there are these experiments that look for like one event in 1 year. So very, very low rates. Similarly, very, very low rates. There are many experiments that look for possible dark matter candidates, or in general, light particles that interact very, very weakly. So it means that you have some sort of a target, and this light particle comes in and it hits one electron, for instance, at very, very low energy and with an interaction that is very weak. So it really takes one electron, maybe with a very small frequency. So these are experiments that are typically on the ground in caves, in environments that where there is no noise at all, there is no radioactivity, nothing happens. And there's really many of them. They use several different techniques. Also in here, there are also experiments that do other things. So they look, for instance, for axions that come from the sun. And then in the giant magnetic field, they convert into photons. And so you have light that appears out of nowhere. So there is really many of these experiments that are going around. This is one example from the xenon experiment that is in Gran Sasso, and is one of those that looks for dark matter. I went the wrong direction. Okay. So all this, what is it getting out? Well, okay, so there is this plot here where you don't read anything, but you're not even meant to, which is the classic LHC product. So this is by CMS, so one of the two biggest experiments of the LHC. And it's a summary of everything that they have excluded. So they look for a kind of particle, I don't know, I want a Z prime here. Well, it's excluded in this mass region. So from 500 GeV to 2 TeV, for instance. And so they summarize everything that has been excluded, excluding, because nothing has been found yet. So there is no evidence for any new particle. So this is what comes out of trying to produce a new particle. So far, nothing, at least up to a few TeV. There are a few anomalies here and there that could be controversial or not. So one anomaly is in the flavor sector. and it is in B decays to B mesons and tau and neutrinos. So there are two different branch ratios that are measured by many experiments, and it turns out that they are a little bit off compared to what you would expect from the standard model. So the standard model would prefer a point that is here, so it's like a 1-1. But what is measured is really far away, and the statistical combination says that it's significantly far away. Although, so the experiments agree with each other only up to a certain point. This is another example, which is from this muon G-2. So this is the gyromagnetic moment of the muon. The predictions of the standard models here, and they're very precise. It's like 5 loop calculations, with several tricks. So it's something that is highly non-trivial. Some other calculations, they use different techniques with lattice, stay a bit on the right, although they have larger bars. And the measurement is quite far away. So the measurement has been like this for a while. We just had an update this year, which was also around this band. So it's really just being confirmed. And there is a very large separation between the standard model prediction and what is actually measured. People are trying to understand if this is in physics, if it's a mistake in the calculation, if there's a problem somewhere else. It's one of the open mysteries. On the diameter search side, also a lot of exclusions. Everything that is colored here is also exclusion. So typically you have these plots where you have on the x-axis the possible mass of the dark matter candidate that you have. To give you an idea of how well informed we are, this is like 21 orders of magnitude, I think. Yes, and this is, okay, only 4. So there are many orders of magnitude on the x-axis, and there are also many orders of magnitude in the y-axis, which is the strength of the interaction. So this is where we look for something that is very light, very weak interaction. Interactions are 10 to the minus a lot. Okay, so they're very, very small. So the exclusion comes from the top, right? So it's easier to constrain first the stuff that interacts more strongly, and then at some point they become so weak that it's impossible to exclude them anymore. So we don't know if there's any new particle here. We have not explored that yet, but these shaded areas tell you that in the future there will be some experiments that will get into that region. And something similar happens here for the dark matter search, which, okay, it's a different parameter space because it's a different model is assumed. But all these experiments have excluded all this region that is green here, and they're going down and down and down until they will reach this yellow region where basically they will see neutrinos scattering off each other, and that's an irreducible background. So this will always happen. So it will be much harder to find dark matter if it's down there. So bottom line, we have not really seen anything yet about new physics. There are a few anomalies here and there, but there is nothing convincing, nothing well established. Okay, so now let's go back to the thing that I wanted to say at the beginning. So I told you this is a bridge between theory and experiment. So I'm going to do first the error from theory experiments to understand what we do. So phenomenology is very broad. It's a very broad field. There are many, many different tasks contributing. So one that is obvious and very, very important is to make theory predictions. So you start from a model, in this case, the standard model, and you have to calculate what would be the cross-section, the differential cross-section of a certain process in a certain experiment. So everything I will say here is very LHC-centric, so I mostly mean at Atlas or CMS. And the example that you see there, this is a natural plot from an LHC experiment, where they're measuring all these data points, all these balls here. And they are looking for the production of the 4 leptons, the one that we drew before. So it turns out that there are many ways that you smash together 2 protons and you get 4 leptons. And some of them you're interested in, some of them you're not interested in. Either way, you need to be able to calculate all of them in order to understand exactly what you're measuring. Because in this case, the signal that they're looking for is the sum of these blue and red lines, so the one that you see plotted underneath. So they want to be sensitive to an effect of that size. And all the other color blocks, they are backgrounds. So there are other processes that produce the same signal, but we cannot distinguish them. And you see that they are like 3 orders of magnitude larger than what you want to observe. So it means that you really need to understand very, very well what we're seeing. You need to be able to make predictions. And predictions are essentially provided by theories. So theories provide the tools in order to run on these aspects. Precision is really crucial. This is an example that I took from a slide that was shown somewhere. This is one of the star processes at the LHC, one of the ones that we care the most about. It's the production of the Higgs boson in gluon fusion. So you have two gluons, and they give you a Higgs boson. And you can calculate the cross-section for this process. And if you calculate it at tree level, you get this number here. So there's a number with a certain error bar. This is something in picobar. Okay. Then you can say, okay, I want to go to one loop in QCD. Let's check what are those corrections. And then you will get the red result, which is already quite far away compared to the initial prediction. You can go to 2 loops. And now people have gone to 3 loops. And you see that now, so the result in pink is the one that actually can be compared to the experimental sensitivity, which is roughly the one that is shown here by this error bar. So the precision of the predictions has to match the one of the measurement. Otherwise, we don't know what we're measuring. We're going to make any statement. And so there is a lot of work that is necessary that goes into this thing. So predictions, of course, need to be made also for beyond standard model stigma. So imagine that you're looking for a new boson, a Z prime that looks like a Z boson, but is a bit heavier. What would it look like? Well, it depends on many things, but once you have fixed a few choices, it could look like this, for instance, like this tiny peak at the end of the spectrum here. Okay, so this is what the experiment is looking for. And from here to there, there's like 10 orders of magnitude. So you need to control very, very well this is a standard model that is still up to there. And then you need to know that your prediction has to be that tiny squirrel down there. And in this way, you can make the exclusion and say, no, I haven't seen. But you really need a lot of precision for this. And this leads, for instance, to this kind of thought. So this is taken from the same publication now. Okay. It's about hypothesis testing and the idea that essentially people compare two hypotheses. They ask themselves, okay, I've seen this data. Is it more compatible with having the particle or not having it? And it's more compatible with not having it until this mass here. And then we don't know what to say anymore because here, essentially, we don't have data anymore. So this we are out of data. So if there's a particle there, we don't know. We cannot make any conclusion. There's also the fact, so there was an example for a prediction for a new resonance. But I told you at the beginning, one other way to look for new physics is to stress test the standard model. So try to see what happens if we change things here and there. So this is a classic example of what happens if you try to change the couplings of the Higgs boson. So each of these kappas are basically some factors that change the coupling to the Z, to the W, to the top, and so on and so forth. So in the standard model, they equal 1. And if there's any deviation, you will find a number that is different from 1. This is a basic exercise of try to find the deviation. If I put in a number and I run a statistical analysis, what comes out? And this is what comes out of the Atlas measurement, for instance. But these predictions also need to be made by theory. So there needs to be some way that we can recalculate all the cross sections and everything, including the effect of this modification. So as you can imagine, there's quite a bit of coding because none of this is done really with pen and paper. There's coding in both directions. So in the sense of producing the codes, there's a few people who have developed these tools, which were also phenomenologists. And there's a lot of coding in terms of using the codes that have been produced. So there are tools that exist for symbolic calculations. So typically these are mathematical packages, most of them. And there's a whole chain. So essentially the idea is that you give it a Lagrangian, it will give you the Feynman rules, and it will automatically calculate the amplitudes for you, and you can square them and get out your result in terms of the masses, STU, and also in the loop functions if we want to go to. But as you can imagine, this is not really so. This is very useful for us to understand something when you want to calculate some process analytically. But when you have to compare to the experiment, what is really needed is to have someone to calculate. So people who really calculate 2 and 3 loops what they do is that they automate their own predictions. So they produce a tool, which then is given to the experiment, and the experimentalists run it. And they produce plots like this, where they take many different Monte Carlo plots produced by different people, and they compare them among themselves and to data. And you see that here all of them are quite precise, and they're all compatible with data within the algorithm. Okay, so a fundamental task that you have, so the phenomenology test is also to guide the experiment, in the sense that there is a lot of feedback in both the directions of theory to experiment and back to theory. So phenomenologists are coming up all the time with new ideas for what to measure and how to measure it. They're proposing new strategies. So there are many questions that experimentalists keep asking us. So for instance, what should we search for? What is interesting? How can you judge? How can we test the standard model in the best possible way? How do we extract most information from data? There's also questions about how do we make our measurements most useful. So the experimentalists publish their plots, but then we want to use them, we want to reinterpret them. And so we can also offer guidance about how the publication of the results. The example that I'm showing here is one semi-recent example of an idea of how we do extract most information from the standard model. It was done by people, some of which are here. So the idea was that people are very interested in measuring the set coupling of the Higgs boson. We have not measured it directly because it's very hard to produce two Higgs bosons. But you could, instead of using that process, you could use other processes where this coupling enters essentially at one loop. So it's kind of hidden inside the calculation. And they estimated that you could have some sort of sensitivity that made projections for some LHC data. So this is all phenomenology work, where you sit down, you calculate, and then you put it in a Monte Carlo, and you produce a statistical analysis, you write down the likelihood, and you get out, and then you can go to the experimentalist and tell them, try this out, because this could be useful. And then they actually did. So there's only 6 years between these two papers, but this is only the latest. So this was actually applied even earlier than that. And experimentalists go out and they do try out the bounds. So the one that corresponds to this suggestion is the one in blue, and it's compared to the sensitivity from the direct search of two Higgs productions, which is still stronger. But the two things are quite competitive, and they can also be used in other setups. Another example comes from so this recent example I was mentioning before of the flavor anomalies. So there are some decays that look a bit off in the rate compared to the expectation. Yeah, I don't see anything here. So people have been looking into those for a while, and they have come up with theories and explanations. And for instance, these people propose that, well, it's probably a weird particle that is called left of quark. Left of quark is nothing like you have ever seen. So it's a strange, in this case, vector boson. So it's a bit like the Z, but instead of coupling to leptons or quarks, it couples to one lepton and one quark. So it weirdly mixes the two things. And they worked out a model about this, and then so they proposed an experiment. They would search for this kind of particle, and so now the experiments are producing plots like this, where they combine different ways of searching for this new particle, and they also check if the particle that they find is compatible with the one that explains the anomaly that was initially proposed for. So this is another example of like continuous exchange. So this happened while the experiment was running, and they came up with ideas and they talked to people and they implemented it. Yeah, I'm gonna skip. Now on the other direction, so once experiments have been, guided a little bit and they have produced the experiment, this is also the job of the phenomenologist to interpret their measurements. So this is the same paper as before, actually, because I think it's a very instructive example, and there aren't many lately because there haven't been so many anomalies. But in this case, there were some anomalies in the measurement. So what these people did was that they took the measurement, and as it was published, and they said, okay, let's interpret it first in terms of some contact interaction, something that is very, very general and very, very basic. And they figured out in this kind of parameterization what would be the value of the couplings that they needed. Then from this, they took the next step, and they were like, okay, now we go to a simplified model. So this is the same left of quark particle that I was mentioning before, we just assume that only the left quark exists and then it has this and this interaction. And then this bounds translate into some preferred value. So what are the couplings of this particle that it should have? And then from there, you can take yet another step, which is much more complicated, which is to actually put this particle inside a very complete model that explains many other things at the same time, and that contains many other particles at the same time. So the model that they built is actually very complicated. And it turns out that in this model, there are other kinds of particles that you can also look for. And so they also calculate the work you need to do in order to find those, and then made proposals to check their ideas. So at this point of going off and trying to make a model that works, it's called model building. It's one of the main areas of phenomenology. Basically, people who do model building, they have this challenge of constructing models that work, so they are theoretically consistent, and they are compatible with observation. So we have we have many measurements that exclude new physics, right? So I just showed you that there are many things that are excluded. So we have really tested out a lot of phenomena. So any new model has to be compatible with that. Typically, new models are motivated either by explaining some anomaly that we see. So this is the scheme of the very complicated model that these people built in the previous slide. Or they are motivated by answering fundamental questions. So in this case, they didn't just want to explain this small anomaly, they also wanted to have a theory of flavor. So explain why we have the three generations, where they come from, what are the roles, why are they ordered in that way, and explain all these sorts of things. Yes, so this is another example from another completely different type of model. This is called the two Higgs doublet model. So if you have the Higgs twice, it is related to supersymmetry, but okay, this is not relevant for now. You just have two Higgs doublets, and this has many parameters. And so what these people did was that they went out and they checked all the measurements that are out there that put constraints on this kind of physics. And they did a scatter plot. So they literally went and said, okay, I take a random value in this parametric space. Is it allowed or not? And if it's allowed, they put it in blue. If it's not, they put it in red, or they just left it blank depending on some selection. But in this way, so they were able to chart everything that is still possible and everything that is not. So this is another typical task that people can think about. Now, going towards the theory, like more and more towards the theory, there is also, a task of understanding deeper implications. So it's not just, okay, I have this model, does it work or not? But also, what does it mean? Is it something that goes farther? So getting out some fundamental information. So the example that I'm showing here is a paper that came out very shortly, like I think 1 year after the discovery of the Higgs boson, so not very long. And what they did was that they realized that once you have measured the Higgs mass, which at that point we had known for 1 year that it was 125 GeV, then you can ask yourself the question of like, okay, if the standard model is the ultimate theory of nature, and there is nothing else, and then up to very high energies, there is nothing else, what happens? Well, you might have seen that there is a phenomenon that is called the normalization evolution running. So the couplings change their values. And this implies that the scalar potential of the Higgs, which is the one that determines that we sit in a vacuum that gives us a mass, this will change shape as we go to higher and higher energy. And you can ask yourself if, the minimum will still be the minimum, or if something changes at the phase transition. And they discovered that we are exactly in the metastable region, which is very singular. So this is a function of the top mass and the Higgs mass. And there were many values for which we would have been safe after arbitrarily high energy, or where, it wouldn't have made any sense that we were safe. And we sit exactly in here, in this tiny spot around here. So this is an example of extrapolating very far that brings up new questions like, can it be? Or does it mean that, this is a proof of existence of new physics, like there must be something else, because otherwise, essentially there would be, a finite probability of tunneling towards a vacuum where we just don't exist. So it's a kind of interesting study that can also be done. And finally, the last thing that I want to mention about things that phenomenologists do is the putting everything together. So there are many experiments out there, and there are many theories, but so it's important to have some sort of common interpretation infrastructure, so a theory framework that is simple enough where we can make sense of many measurements at the same time. We have to check that different measurements that are done actually agree with each other, so we need to have a metric for that. And so the way that this is done typically is to do this global statistical analysis. So when people have decided the range of parameters and they put in all the constraints at the same time, and they want to see complementaries and also if everything is consistent. These are done in many, many fields. So one example is the neutrino measurements. These are likelihoods that would take a while to explain, but so these are measurements of various values of the neutrino oscillation parameters. This is the same plot that I showed before about searches of axion-like particles. So in the space of coupling proposals versus mass, what do we know? And we discovered there's a lot of complementarity between different experiments. Each of them covers a patch. And overall, we have excluded a lot of the parameter space. And there is also on the LHC front, something that is called a Stanamale effective field theory that I will show you in a second, which is kind of the evolution of the kappas, as I showed you before. So these are parameters that tweak a bit the interactions of the standard model. And there are many, many of them. So these are 54, I think, but it's even more. So they limited themselves to 50. And you can, collect many hundreds of LHC measurements, put them together and realize which of them are constrained, which are not, how well do we know them, and how they will improve in the future. So there's a last point about, these techniques can also be applied to making prospects for the future. So the plots that you see here are very similar to those that we showed before, but they are done estimating the sensitivity of future colliders that have not been built yet. It has not even been decided that we will build them. So this is a kind of plot that helps us decide if it's worth building a new collider in 40 years or 60 years or not. This is for deviations from the standard model, and this is for the sensitivity to particular masses, so to particular new physics states, in this case, scalars. And it's made to showcase that the collider that collides muons, for instance, would be really, really powerful, although technologically now it's very challenging. Okay, we got to the point where you're wondering, what do you do? Okay, I can tell you in a very few slides. So I work on this thing that I showed you before. So it's called Stanamale effective field theory. And the idea, I don't know if you have seen effective field theories in the courses yet, but is that you add interactions to the standard model that have dimension larger than 4. And this gives you a catalog of effects that are purely beyond standard model effects. And the idea is that if you go and you measure the couplings of all these interactions, then you can learn something about new physics, because depending on which one turns on, then it is a different kind of particle that has generated it. There's more of those. So in here, there's a lot of work to be done. So as a phenomenologist, here are some examples of things that people do with my work, but I'm not the only one, definitely. So there are some semi-analytic calculations that one can do. They're very useful in this case because all these many parameters, sometimes they have to cancel exactly, or sometimes the analytic form is very informative about what you would expect. So there are some calculations that you can do by hand, but as we saw before, not everything can be done by hand. So I also have developed this smart team thing, which is an interface for a Monte Carlo generator. So it's not a Monte Carlo generator itself, but it's kind of a plugin that uses another one that already exists, and basically contains all these parameters of these models, and now the experiments can take them and do the simulation for all these effects, and you get something like on the right side on the top. So this is for the production of 2W and 2 jets, okay? Some process at the LHC. And you can check the standard model predictions are the solid ones, and then if you put in your X as an effect, you will actually predict that you have the blue line. So knowing this information, then you can go and you can put some bounds, and you can have some sensitivity studies for how sensitive this particular process would be to this kind of operators. You can also ask the question of how well can I distinguish the two parameters that are on the two axes. And of course, there are global analysis, so that is my version of the plot. This is much smaller than the one before. But this was a few years ago, so you can also study, let's say, specific sectors and try to work out specific ideas that can improve the knowledge of certain parameters or distinguish ways to distinguish the different parameters, try to come up with new ideas to propose to the experiments about how to do this. And you can also so compare the net parameterization with specific models. So what we did here was that so these all set of parameters in effective theory can be related to the parameters inside a specific model that you want to choose. And so we use the constraints that come from this kind of general analysis, and we map them back to the bounds of the model to see how much we are actually learning about that one in particular. At the moment, right now, I am actually doing a little bit less Pheno. It is Pheno still, but on the very forefront of thinking. I'm wondering if it's possible that this whole thing is actually invalid. And as you can imagine, there are many basic questions, like for instance, how does that happen? What do we mean? And how do we even notice, like, what would be a signal that this whole construction is coming down? And this, I would take ages to explain, but it involves a lot of differential geometry methods. And eventually we'll come back to phenomenological predictions, but this is an example, although you cannot really understand from here, of interplay between some more formal theory and actual phenomenology. So try to understand the theory first and then come back with, okay, what do we need to measure? And the very, very last thing that I'm mentioning, this is probably my last slide, is something that is not this effective theory, it's another one, so on axial-like particles. These are part of the particles that people are looking for, the light ones. So there are constraints on the parameter space of these objects. They're the ones in the plot that I showed you before. But not all the coordinates are very constrained. So particularly these particles are not so light, so there is quite a bit of space. And so I've been also interested in coming up, let's say, with new ideas for how to search for them at the LHC. So this is an example of how a signal could look like. And also to have new strategies, for instance, if you put them in a loop, what happens, and try to get out more powerful constraints from there. And this is it, I'll wrap it up. So it was a very challenging task to give you more or less an overview of how many things there are in phenomenology, but I hope I've piqued your interest in at least a few of them. So I should also say that several of the things are similar to the things that I showed are also done by people who participate in the master, people in Dortmund, Vermont, and people here. It is an interesting field where you can get the possibility to connect to very different topics, to talk with experimentalists, to make a lot of friends everywhere. And also to use a lot of tools in a different way. And I think it's fun, and it was something that really worked. So thank you here. And if you have any questions, I can stay another bit without.